So if a number, this is a remainder theorem, sorry. If a number c is substituted for x in a polynomial f of x, then the result of c is a remainder that would be obtained by dividing fx by c, x minus c. That is, if fx equals x minus c times a quotient plus a remainder, then f of c is equal to r. So what that means is that if I had a linear factor for the most part, I was trying to divide by that to see if I had a zero. My remainder would be the same thing as if I just plugged that zero into my function. So if f of c equals r equals 0, so that means I put that c in and I get a 0, then c is just a 0 of fx. So as an example, these last two problems we did. So if I want to see another way what the remainder would be, so we did this division, we got a remainder of 0. So f plus 1 would mean that it's the same thing as saying that I have a 0 if this was a factor at x equals -1. So if I just replace all my x's with that -1, like I said, just think of this as being like f of x. Well, if I do f of -1, what we see we get here is that we'd end up with 5 times 1. We get -3 here, -2, 5 minus 5. We get 0 again. Okay, so what we're seeing here is that, like I said, if instead I had just, instead of using that linear factor to get my remainder, I could have just used, like I said, linear factor is x plus 1. If I set that equal to 0 and solved it, then that would have been x equals -1. I plug the -1 in, I still get that same remainder. All right, and then this one, when we had done it, we had a remainder of 1. So if I took 3x minus 2, set this equal to 0, what it would equal is that x would be 2 over 3. So let's pretend this is just a function g of x. Well, let's say g of 2/3 means I'd have 6 2/3 cubed plus 11 2/3 squared minus 31 2/3 plus 15. So when I did this in my calculator, this actually did come out to 1. So that's what remainder theorem is saying, is that instead of using that linear factor to find the remainder, I can set it equal to 0 like I did here. And then this number I can plug into the function, and that will also give me my remainder as well. So another thing we get out of this is for a polynomial f of x, if f of c equals 0, then x minus c is a factor of fx. So what we have here is a way to figuring out what our linear factors would be by simply we can like test and see if a point is actually a 0 for us. So we're going to use remainder theorem and factor theorem to show whether x minus 3 or x plus 3 is a factor of x cubed plus 2x squared minus 15x. If it is a factor, rewrite the polynomial in factored form. So that will require us to do polynomial factoring problem. Actually, no, we can get by without that. We just would know what ones and zeros were, but we could use polynomial factoring on this. The same thing for 12 is try those 2 points and see if one of them is a factor. It could be both of them. It could be neither of them. It could be one of them. So take a moment and try 11 and 12. And like I said, if you find a factor, then try to factor the rest of it. Okay. So if I have x minus 3, and I want to know if that's a factor, I set it to 0, I would get x is equal to 3. So what I'm going to do here is that I'm just going to replace all my x's now with 3. I'm going to see what happens. So if I do that, I get 9 plus 2 times 9 minus 45. 9 plus 18 minus 45. Do this. I have to write down here just a little bit. I was trying not to, but 27 minus 45. So what we're seeing here is this doesn't look like it's going to be a factor for us. So let's try this one. So we got x plus 3. If we set that equals 0, we get x is equal to negative 3. So we're going to plug this all in again and see what happens. So all my x's are now replaced with a negative 3. Oh, you know what? I made a mistake on that last one. Well, let me do this one again. I just realized that I think I squared when I was supposed to cube. So we're going to try this one again. So we had 3 cubed plus 2, 3 squared minus 15 times 3. So this would have been 27. This would have been 2 times 9 minus 45. 27 plus 18 minus 45. So if we had 27 plus 18 is going to be 45 minus 45, that gets me 0. So that tells me that this is a 0 and that this is going to be one of my factors. So let's try the other point, the negative 3. So we'll erase this and then we'll put in that other point. So I have negative 3 cubed plus 2 times negative 3 squared minus 15 times negative 3. This is negative 27 plus 2 times 9, because that will be positive. These will give me a positive 45. So I'm going to have negative 27 plus 18 plus 45. So what you're going to end up with is you're going to have negative 27 plus 18, which is going to be equal to 9 plus 45, which is going to leave you with 36. So this one here, not a 0 and not a factor. Okay, so like I said, we could just factor this. I'm going to use the polynomial long division because I'm preparing you for like harder problems that you would see. But now we know that x minus 3 is a factor. So we are going to factor it out of x cubed plus 2x squared minus 15x. So if we do that, x goes into x cubed, leaves me with x squared. Multiply x squared to x, multiply x squared to 3. Remember, we're subtracting. So I'm going to be left with 5x squared, and we bring down to negative 15x. Divide x into here, we get plus 5x. Plus 5x times x is 5x squared, plus 5x minus 3 is negative 15. Okay, no, I'm good. I thought I was missing something there. Yes, and then that will leave me with 0. which we knew should have happened. But now what we see here is that I can take 3x squared plus 3x cubed plus 2x squared minus 15x is equal to x minus 3. And then what was left over was x squared plus 5x, which we can factor further. So this I can factor an x out of, leaving me behind an x plus 5, and then I'm just writing the x minus 3 down here. So this is part of the point of using like remainder and factor theorem, is that if we do actually find a 0, then we can use the factor, the linear factor, to factor it from the polynomial to make it something that's easier to factor. Because we don't factor a lot of third degree polynomials. It's not something we practice a lot. Like I said, there was another way that we could have done this. We're just doing a little more complicated way right now. But it's to help you factor things of higher degree so we can start factoring out terms until we can get something that's a little more manageable and easy to us to factor, something like a quadratic. All right, so once again, we have two choices. We want to see if x minus 3 is a factor. So if we set it equal to 0, we'd get x is equal to 3. So like I said, think of this as just being f of x equals x cubed plus 5x squared plus 3x minus 2. We want to figure out what f of 3 is. If you do that, what you would find is that this one is going to be 79. If we do, so like I said, this is not a 0. Meaning this is not a factor. All right, now let's do the other one. So the other one is x plus 3. We want to see if that's a factor. So we set that equal to 0 and get x is equal to negative 3. So that means we need to figure out what f of negative 3 is, which would give me 7. So once again, that is going to be not a 0. And this is going to be not a factor. So one of the things we're going to do here by the end of this set of lessons is being able to figure out what zeros we need to, or what numbers that we should try dividing by to actually figure out if it is going to be a factor or not.